She heads the Hispanic clinic at MGH, so they're going to actually have a clinic devoted to individuals of Hispanic race who have special needs in and of themselves, as well as language needs. So she's heading that up, and she's also a neuropathologist in Dr. Hyman's lab, doing some wonderful, wonderful work on a brain that you give us. So today's.
I'm really happy to be here with you today and to have this opportunity to thank you in person. First of all, for being part of our team. And secondly, for working so hard with us in our search for a cure for Alzheimer's disease and related disorders. And what I'm going to try to do in the next few minutes is share with you some of the important things that we've learned about brains with Alzheimer's disease and other disorders, thanks to those people and their families who have understood that brain donation at time of death is one of the most important and generous gifts that a person can give. But first of all, let me just tell you a couple of words about this German physician, Dr. Alzheimer, who's best known for having described the disease that bears his name, but he's also known and acknowledged for having made some very important contributions that have forever changed the way we think about mental diseases and the way we treat patients with mental conditions. When he was a young doctor, he joined this institution for lunatics and epileptics, and I think the name says it all. He was really a pioneer, and along with his colleagues, they really transformed this institution into a proper psychiatric clinic, making it a care facility. So one of the very first things that happened thanks to this doctor and his colleagues was that restrictive measures for reducing agitation in psychiatric patients, which were extremely common at that time, were abandoned. But perhaps even most importantly, he worked really hard to disprove the widely accepted theory at that time that claimed that mental diseases were the consequence of traumatic childhood experiences. He believed that brain disorders were in fact the result of organic brain lesions, and he worked extremely hard to prove that by using and studying brain tissue samples. So he was a doctor that during the day would take care of his patients, would talk to them, would write exquisite notes about the observations he made on these patients, and then during the evening hours, he would spend a long time with his microscope looking at all these brain tissue specimens from autopsy, trying to find what were the lesions that were causing the symptoms on his patients. And let me tell you that he could not have been more right, because time proved that autopsy brain tissue from individuals who are carefully observed, carefully evaluated from a clinical point of view while they are alive, would lead to most of the main findings in Alzheimer's disease. So in 1901, this patient, Augustine, was brought to the institution by her husband. She had developed a few years earlier the first symptoms of dementia, including loss of memory and delusional thoughts, and Dr. Alzheimer took over her care. He followed this patient for several years, and when the patient died, he was able to look at her brain. And this is what he saw. We've already heard a little bit of this from Dr. Hyman and Dr. Sperling. But let me just remind you that what he noticed were two different types of lesions in the brain. The first one is here, are these deposits of aggregated material that at that time he really didn't know what it was. It would take several years for us to figure out that these senile plaques are primarily made of a small peptide that we all have in our brains that is called beta amyloid. And they form these deposits between neurons. And he also noticed this second lesion in the brain of his patient, and in this case it was inside the neuronal bodies and had this morphology resembling a tangle, and that's why they are called neurofibrillary tangles. And again, only many years later, we would get to know that these tangles are mainly made of a second protein that gets abnormally accumulated in Alzheimer's brains that is called tau. Along with these plaques and tangles, in Alzheimer's brains there is a progressive and very significant loss of neurons and their connections. As you know, they are called synapses. And that's why you see this brain shrinkage in Alzheimer's brains when you compare them to healthy, normal brains. And also, in addition to the loss of neurons and their connections, we get to see a very prominent inflammatory response in the brain of Alzheimer's patients, mainly driven by the abnormal reaction of that other type of cells in the brain that Dr. Sperling was talking about earlier that are called glial cells that we are still trying to figure out how they contribute to Alzheimer's disease. What we know is that their normal function is mainly to protect and to provide support to neurons, a function that perhaps is lost in Alzheimer's disease. So, probably because Augustine was actually a young patient. She was only 51 when she was brought into the institution. She died when she was 55. Sadly, Alzheimer's disease went unnoticed for many, many years. It was considered a rare condition, typically affecting young people. So it was going to take another 50 years before the first large scale autopsy studies were done on elderly individuals. And from those studies, we have learned very important things. The very first one is that plaques and tangles are not a rare event at all. In fact, they are quite common in the aging brain. So if you reach the age of 70, 75, many of you will have at least some plaques and tangles in your brain. And of course, the more pathological lesions, the more plaques and tangles that you see in a brain, the more likely that person has been living with Alzheimer's disease. So that's the first thing that we've learned by looking at the brains. Now, with more work on autopsy brain tissue and also with more advanced staining and pathological techniques, we have also learned that there are different types of dementia. The most common one is Alzheimer's disease, but there are also other lesions that can cause dementia, including Lewy body lesions, sometimes seen in Parkinson's disease, stroke, and vascular problems, frontotemporal dementia, and etc. Let me tell you that sometimes it is quite challenging actually to distinguish from a clinical point of view what type of dementia a patient has. And in fact, brain autopsy is the only way to confirm a true diagnosis of Alzheimer's disease. And even in the best hands, and I'm now here talking about physicians who have a lot of expertise in the care of people with Alzheimer's disease, the accuracy of the clinical diagnosis is about 85 to 90%, but not 100%. Now, you can imagine that studying disease brains is really, really important if we want to correlate those lesions to and link them to the clinical symptoms that an individual may suffer while alive. But of course, taking a look to healthy brains is as important as studying disease brains. And this is one of the studies where, that also has taught us very important lessons. This is a long-term study that started in 1992 on nearly 700 older school sisters on Notre Dame, aged 75 to 102. And these nuns, just like you now, they underwent very careful clinical evaluations trying to detect the first signs of dementia. They all signed up front for brain donation at time of death. So some of those women have already passed away, and the researchers have been able to connect that phenomenal amount of clinical information that they have on these women to with the stories that their brains have to tell. And this is really the way we think about these diseases, to try to move forward and learn more about them. So this study, along with some other studies, including those that are conducted in our own center, actually we found there some interesting surprises. So the first one, you already know about this because Dr. Sperling and Dr. Hyman already mentioned. The disease starts in the brain more than a decade before you develop symptoms, probably even 2 decades before you develop symptoms. So this is one of the challenges, the big challenges that Alzheimer's disease is posing on us and our research. On the other hand, if you may think about it as an advantage because you have this really long window of opportunity to intervene, to think about novel therapies and test them during this long asymptomatic phase of the disease. In fact, I did actually my thesis with Dr. Hyman many years ago, and one of the things that we discovered was that in some areas of the brain, you've lost as much as 1/3 of your neurons by the time an expert neurologist can start thinking that perhaps, just perhaps, something is not going well in your brain. So again, I mean, it's a long, silent phase during which the disease goes pretty much unnoticed. Now, the other very interesting and surprising finding from this and other studies is that about 1/3 of the brains from some of the nuns that did not have any clinical symptoms of dementia while alive had all the pathological signs of Alzheimer's disease at autopsy. So, if we think about this, of course, the question that comes next is this one. Can we assume that all the individuals who have plaques and tangles in their brain will actually develop symptoms of Alzheimer's disease if they live long enough? Or is it possible that perhaps at least some of these people may have features in their brain that are going to make them resilient, somehow are making them to be protected against the toxic effects of Alzheimer's lesions, and they're just going to remain cognitively healthy throughout their lives. Let me tell you something, we don't have an answer for sure, and this is a very, very critical answer that we need to find, especially now that we've heard from Dr. Sperling, the neuroimaging field is moving really fast. For the first time ever, we are able to see not only plaques but also tangles in the living brain, and we're beginning to notice that some elderly individuals have both plaques and tangles in the brain and yet do not have symptoms. So again, trying to understand if any of those people could be resilient to these lesions is going to be very, very important because that probably is going to give us some clues for the design of novel protective therapies. I'm just going to use this analogy that is coming from the AIDS field that I'm sure you are all going to understand very well. It turns out that many forms of HIV, as you know, that's the virus that causes AIDS, use a receptor that you see here in yellow that is called CCR5 to enter and infect white blood cells. Well, several years ago, someone figured that in some rare cases, there are individuals who carry a mutation in the gene that codifies for this receptor that was protecting those people against some form of the HIV infection. So even if the virus was in their bloodstream, that virus could not get into the cells and infect them. And actually, I'm just using this as an example to say that this discovery in a very small and rare population of individuals has validated a new target for AIDS therapy. And some of the drugs that are now being used in all AIDS patients are based on this rare observation. So we're taking a very similar approach. And one of the projects that we are involved in our center is trying to figure out whether some people could be resilient to Alzheimer's pathology in their brains. And these cases, let me tell you that they are rare enough. So we figured that we really have to, we have joint efforts with other Alzheimer's centers to get enough brains so we can study them. Now we have over 60 brains, and some of those are from people who at time of autopsy were found to have lots of plaques, lots of tangles in their brains, and yet they never developed signs of dementia while alive. So, of course, the first thing that we did was to actually count those plaques, those tangles, and compare the amount of lesions that these brains have to brains from patients with Alzheimer's disease who died at advanced stages of the disease. And after counting these lesions, plaques, and tangles, we came to the conclusion that those resilient brains have as many plaques and as many tangles as those other individuals who died being profoundly demented. However, let me just give you a quick idea of some of the differences that we are beginning to see in these brains. We counted neurons in those resilient brains, and we found that the neurons and their connections are still alive. So for some reason, even though the brain is full of this junk, those neurons in these brains have managed to survive and of course keep functioning really well till the end. One very interesting finding is that along with that enhanced neural survival, we see in these brains very little signs of inflammation as opposed to a robust inflammatory reaction in the brains of people with lots of symptoms and lots of plaques and tangles. The other difference that we've seen, and this is also very interesting, is that in addition to plaques and tangles, in the brain there are like small clumps of the same proteins that form those plaques and those tangles, beta amyloid and tau. These are soluble small assemblies of these proteins that we don't see when we use routine staining techniques. We only detect them when we use more sophisticated techniques in the lab. Well, it turns out that even though the number of plaques and tangles again is similar between these two groups, the amount of those small soluble clumps of A-beta and tau in the Alzheimer's brains seems to be significantly lower than in demented Alzheimer's cases. So, again, I mean, we are beginning to think that perhaps rather than what we see, rather than what Dr. Alzheimer saw on his patient's brain, it is what until now we couldn't see, these small clumps of these proteins that could be more directly involved in the loss of neurons and in the clinical symptoms of dementia. This is just to give you a brief idea of where we are right now. We want to collect, of course, many more brains. We want to understand, in depth what are the mechanisms behind, again, these small differences that we are beginning to see in these apparently resilient brains, because, again, our hope is that this may actually tell us where to go with our therapies. So, I know that more than half of you sitting here have already agreed to donate your brains at time of death. We can thank you enough. Of course, I hope that it's something that we won't have access to in many, many years from now. But for those of you who are still thinking about it, considering this as a possibility, this is really the message I want you to take home today. I hope I have convinced you that your brain is a priceless donation to science. Like many of you, I have kids, and I hope someday to have grandkids. And just like you, I think my colleagues and I want to make sure that Alzheimer's disease does not continue stealing from us and from the next generations one of the biggest treasures we have as human beings, which are our memories. But what I also want to tell you is that while we find the cure for this and other diseases that are related, and I'm sure we will, we are going to continue to take very good care of all those patients and their families who are already suffering the consequences of these devastating disorders. And I thank you very much for your attention, and I'll be happy to take your
Yes, when you talk about issues of inflammation, which turn up in heart disease in this, is there any correlation with people who have a history of taking anti-inflammatories, aspirin or and other things?
Well, actually there have been a number of epidemiological studies, meaning those studies who actually ask people what have you taken, many years ago as for medications. And there was a fair amount of literature supporting the idea that those people who were on some anti-inflammatory drugs, not aspirin, but other types of anti-inflammatory drugs, had a lower risk of developing Alzheimer's disease later on in their lives. And based on those observations, a number of clinical trials were run using anti-inflammatory drugs in Alzheimer's patients. All those trials, unfortunately, gave pretty much negative results. And of course, the question is, as for many other medications that have gone into clinical trials and have failed, is it possible that you are getting there too late? I mean, again, just remember that by the time you start having your very first symptoms of dementia, there is already a lot of neuronal loss in some areas of the brain. There is already a lot of signs of inflammation. It's just very difficult for me to think that any drug is gonna, do a good job, like a really good job at that time, at that point.
So with respect to the Sisters of Notre Dame study, where they found that 1/3 of the brain that had showed the typical Alzheimer's plaques and tangles on autopsy, that those individuals did not were asymptomatic during their lifetimes. Do you think that glial cells, do you think that the glial cells play some role in conferring that resistance? I know what you said about the CCR5 studies as being perhaps more productive of that, but just looking at the glial cells, and does amyloid plaque grow on the glial cells? Is it attached to it?
Okay.
Or on the person?
Okay, so I definitely think that we should be paying attention to glial cells. I mean, one of the differences that we've seen here, you have an example of people without plaques and tangles. These are brains from people with tons of plaques and tons of tangles. And what you see here is a staining for astrocytes and microglial cells that are reactive. And just by eye, I mean, we've quantified this, and of course there is a significant difference. But you can tell just by looking at these pictures that there is a lot of more reactive astrocytes and microglial cells in those individuals who had a lot of plaques and tangles along with clinical symptoms of the disease. Now, what does it mean? There is definitely a difference in the glial reaction between individuals with and without symptoms, with the same amount of plaques and tangles, whether these glial cells in these individuals are healthier for some reason than in Alzheimer's disease. So again, nobody knows for sure how Alzheimer's disease affects the function of glial cells other than, they react. They are becoming reactive, and there isn't that many studies, telling us how glia participates in Alzheimer's disease, whether glial cells could be having a deleterious effect on neurons because they are losing a function that they are normally supposed to be covering, like providing that support and protection to neurons. Are they dying themselves, some of them at least themselves? There is little research, unfortunately, on this population of brain cells today. Maybe because, until now, neurons are the important, have been considered to be the important populations of cells in the brain. But definitely, we should be paying attention to these glial cells. Now, glial cells, and especially microglia, they've been shown that they have the ability to clear amyloid from the brain. Now, let me tell you though that in Alzheimer's disease, despite having a lot of reactive microglia, there are a lot of plaques there. So clearly, for some reason, they are doing a poor job in Alzheimer's brain. So again, whether they are gaining somehow a toxic function that is adding just more damage, when trying to help neurons, they are just, releasing also some molecules are called cytokines that may actually be deleterious on neuronal survival and function, or they are again like losing what it's normally their housekeeper function is still a question. But I think that we should start thinking about how we can understand better what's happening to the Alzheimer's disease, and some of the therapies in the future may actually have to be cell-specific directed. So why not? Healthier glia, I vote for.
Hi, I'm in a study at BU. I hope that doesn't make me a traitor. And we're apparently focused on Parkinson's, and the testing is completely different from this, and I just have to say it gives new definition of the word boring. But is there any relationship, or is that worth?
I just want to make sure I understand your question. Are we talking about clinical evaluations, or are we talking about what we see in the brain? Because both are different, actually.
They're exercise to do mostly on computers. So
perhaps the reason the person
it seems to focus something on with your eyes.
I'm afraid I'm unfamiliar with that. But, we're going to be breaking up soon into small groups. Come to the group and ask me the questions so I have a little bit better understanding of what you're asking, okay? I think what we're going to do now, since it's 11:30, is we're going to give you an opportunity